Good morning, everyone. We have Faisal Haq here. He's the founder and CEO of Empire Technologies. Faisal, welcome. If you could please introduce the topic.
Thank you, Rahil. Today we will be talking about post-silicon testing and debug and Empare's solutions for that.
That's amazing. People would love to learn about your background and your experience.
Yes, I started at Intel where I worked on processors, cache subsystems, and datacom components, and I went through a few companies. Then I ended up at Growth Networks, startup which was acquired by Cisco, and we started working on Cisco's core routing at that point. While at Cisco, we launched the art of verification Vera, which is considered one of the industry's two classics on verification. And also while at Cisco in 2003, I helped create and launch System Verilog. I was the chair of the System Verilog Association Subcommittee. In 2005, our product Cisco CRS-1, which is a 2 terabit router, came out. In 2012, I was at Qualcomm, and we led the development of uh, Qualcomm's first handset LTE modem. In 2022, we founded Empire.
That's a very impressive background and journey. Great.
Thank you.
So, how to handle design complexity?
So in today's designs, really face two challenges. One is that they're chiplet. More and more of these are chiplet based, and secondly, that they have multiple high-speed interfaces. So chiplet based, what that causes is limited probe access, so you can't probe inside, and secondly, very limited visibility. Because the high-speed interfaces, you're typically running at very high bandwidths, such as terabits per second. And typical interfaces that are high speed are today UCIe and Ethernet. So in those cases, line rate traffic generation becomes a problem. Because these are high speed interfaces, each of these is layered. In each layer has own FSM. Typically, they're broken down into a protocol layer or link layer and a SerDes layer. Um, and because they're SerDes based, the external signals are analog. So a logic analyzer won't help you see what's going on inside the code.
Right. And how does the post-silicon testing happen?
So, the post-silicon testing is really mostly in, they do, for example, in bring up case, they'll bring up the design and verify default values, read and write registers, bring up the links, go through link training. Finally, once bring up is done, they'll go through feature by feature testing of all the functions that are on the chiplet or the chip. Typically, they'll go through each chiplet by chiplet and then do uh, feature by feature on each chiplet. Um, then they'll once they've done that, they'll go through data integrity testing, which primarily involves loopback testing and some known pattern based testing, finally injecting errors and seeing the response to that. And at the very end, they'll start doing performance testing, which is throughput testing as well as bit error rate testing.
Right. And what are the challenges for testing?
So as I said, the two main interfaces that today's chiplets have is UCIe and Ethernet. Ethernet is 1.6 terabits. Um, so in UCIe, you have a high-speed SerDes, which we mentioned before, and that brings its own set of challenges, such as signal integrity, lane skew, deskew, jitter, and equalization. You also have an advanced 3D IC type of chiplet packaging, which limits probe access. Um, and then you have, because this you have limited access to observability, and then because it's broken up, it's a layered protocol. You have, physical layer and protocol layer issues. In the protocol layer, you look at flit issues, flow control, retry logic, and then link training. Similarly, on the 1.6T Ethernet, you again have a high-speed SerDes, again with longer reaches and limited observability, and they have physical layer and MAC layer. On the physical layer, 224G SerDes, signal integrity, clocking and jitter management, and then lane alignment. In the MAC layer, you have to do auto negotiations, flow control, packet CRC, and retry logic if you have LLR MAC. Then we start talking about line rate testing, which basically means you do full bandwidth testing and then fault injection at the end. I mean, the main issues with this is, again, you have limited probe access, so you can't see inside, and also line rate testing requires one point traffic generation at 1.6 terabits, which is a really difficult problem. So, in conclusion, both of these require on-die BISTs.
Right. And what are the debug challenges?
Okay, so from debug point of view, like we said, debug is about visibility. And so visibility inside layers is a challenge. The biggest challenge is, first of all, stopping the machine, the chip, or the logic at the point of error. Because typically, if you don't have that control, the clocks will continue to run and it will stop, whenever the test ends, and there'll be millions, maybe billions of cycles later. So retracing back to the point of failure is very difficult. So breaking on error is very important, and then the visibility at that point, once you've broken, then you look at inside layer challenge, and link failure is also very difficult to debug. So you need to look at state machines, link state machines, and link state. Both of these become challenges for UCIe. For Ethernet, visibility inside the Ethernet MAC is very difficult, and that makes packet errors very hard to debug. On the MBA side, which is AXI and HB, you'll get random bus hangs and you'll get transaction errors. Debugging those is a challenge. So, to summarize, in your debug requirements, you must be able to observe state inside the chiplet. You must have access to signal visibility, which means logic analyzer type functionality. And on top of that, you want to be able to trace transactions across protocols, and you want to be able to break at certain points, programmable points, where you can freeze the logic and look at data points. And you want to be able to trace data flow, and finally, and not this is actually probably the most important, is halt upon error.
And what are the failure domains?
So I think it's important to understand failure domains when you're debugging. Um, in UCIe, you have really three major types of domains, failure domains: flit errors, PI errors, and transaction errors. And flit errors are really at the the protocol or die-to-die layer, and they really involve retry counters, link resets, and flow control. The five failures are typically, depending upon high beta rates, typically depend upon issues related to signal integrity and sideband negotiations, or stuck FSMs, and actually finally the parameter mismatch, in which case both sides of the UCIe must agree on the parameters, and if they don't, then you will not be able to communicate. On transaction side, you can have read and write that fail, that go across the UCIe. So you have to check the protocol level failure, what's causing that failure, and check the address mapping. On the Ethernet side, you have two types of errors: link errors and packet errors. So link errors typically involve either photonics issues or signal integrity issues or equalization issues. On the packet errors, you can have CRC errors, interpacket gap violations, underflows, overflows, packet drops, and idle. That means no traffic coming, even though you're sending data. So those are some of the challenges, failure domains that you'll see that when you're testing silicon.
Right. At the system level, how does it perform?
So this system, this shows a solution to these problems using what the Empare solution is. So one, we have a very high speed traffic generator, which we call Genesis. That's a 1.6 terabit generator that drives the Ethernet MAC in test mode. And then we have a debug engine, which gives you visibility, which can halt on error the system, or the chiplet, I would say, halt the chiplet on or the function, actually halt the function on error, and it would then allow you to access state inside the relevant uh, controllers to see what's going on.
Right. Is it scalable?
Yes, that's a very good question. So, we offer in multiple bits. You can have multiple bits or multiple traffic generators per chiplet. Only one debug engine because you don't need more than one. And we can have multiple chiplets. All of this the entire system can be accessed by one diag running on the host. Um, and that architecture, and it gives you an incredible level of visibility and incredible level of bandwidth.
Yes. And what would be the features of the Ethernet packet generator?
So Ethernet traffic generator, like I said, it's capable of 1.6 terabit in various modes. It can generate the Ethernet standard Ethernet frame sizes and support CRC poisoning. It's a very scalable architecture. We support up to 64 bits in a single chiplet and 256 chiplets in an SoC. It runs at 2 gigahertz. So per bit, we do 1.6 terabits of traffic. Per chiplet, we can do up to 102 terabits. And per SoC, 26 petabits. That's a huge amount of traffic.
Well, and if you can share a little bit more about Prism.
Yeah, so Prism supports multiple protocols: Ethernet, Ethernet with LLR, UCIe, AXI, and AHB. It has a logic and capability which will allow you to trace up to 128 signals from each of these interfaces. It has built-in protocol checkers for Ethernet, UCIe, AXI, and AHB. In addition to that, you can set hardware breakpoints where you can freeze the logic. It'll also halt an error where you can freeze the logic again. It supports single-step execution. And you can read and write to CSRs. You can read and write to memory. We already talked about run, halt, and reset control, and it can do basically transaction level capture at each of the protocol levels. It has protocol checkers for each of the interfaces we mentioned. It has a circular trace buffer that allow you to dump data from memories and registers and dump it to the outside. Um, and then it has multi-event triggering. So basically, it can see a sequence of events before it trigger. So typically today, mostly you have um, Boolean expressions as triggers, but this is over time, like A followed by B one cycle later to C followed by 3 cycles later, a sequence of events that can cause a trigger. And it has performance counters and fault injection. Basically, I mean, a pretty rich set of features to allow you to debug today's very complex designs.
How would you summarize your insights?
So I think the key takeaway is, at today's speeds, an on-die traffic generator is mandatory. And that we use the word missed here. And I think given the complexity of the interfaces, an on-die debug system is also becoming mandatory. Prism provides the debug capability, and Genesis provides you with the traffic generation capability. Um, I mean, we talked about the various challenges UCIe faces, both at signal integrity level and at the protocol level, right? It's got a lot of testing challenges. Um, and you have signal integrity, fleet assembly, flow control challenges. You have protocol level visibility, state machine accesses, credit counter flows, right? All of these are major challenges for testing and debug with UCIe. For Ethernet, similarly, you have signal integrity, auto negotiation, link training, line rate traffic generation, visibility inside the MAC layer, packet either isolation, CRC errors and IPG violations. All of these are major debug issues. Um, and both Genesis gives you the visibility, and no, sorry, Genesis gives you the traffic generation, and Prism gives you the visibility for each of these interfaces.
Right. How does it connect with the products and services that Empire is offering?
So yeah, both Prism and Genesis are part of our test and debug course. Um, and we will be offering additional BISTs in that line. Um, in addition to that, we also sell verification IPs. Those are listed here. I'll not go over all of them. And finally, we also provide services, both UVM-based simulation and formal verification services.
That's amazing, Faisal. How can someone contact you?
So my LinkedIn address is provided above. You can use that to connect to me. If you have questions, you can send emails to the address provided above, or you can go to our website and send an email through that.
Thank you, Faisal, for sharing your wisdom and experience with us.
Thank you.
Thank you, everyone.